Hey everyone. Hopefully by now you've read through the PowerPoint, copied down some of those notes. The purpose of this video is just show you three of the most common three-body diagrams that you'll see, kind of talk our way through those, some of the situations and that kind of thing. So we just start off by numbering these 1, 2, and 3, and that gives us a way to communicate back and forth in terms of which of these diagrams matches up with the problems that you'll be working. So number one's the easiest. It starts off with a horizontal surface. Draw our object in here and our dot for the center of mass. From here we just kind of label the common forces. So we know gravity has to act straight down, so we can label Fg. Normal force is perpendicular upwards from the surface, so that's Fn, that's the ground pushing back up on this object. And then if something were happening in the horizontal direction, so like if this thing were actively being pushed to the right, then that would be our applied force. And if it's moving to the right, then we know friction has to be acting to the left. So that's kind of the setup for the first diagram. If you have a situation where the applied force here would be greater than the frictional force, you could actually draw a longer arrow. That would mean the object would be accelerating. Versus if the thing were moving and all of a sudden it encountered more friction, then this arrow would be longer. That would mean the object would be slowing down. So the lengths of these arrows can be representative of the amount of force that's being applied to the object. Just something to keep in mind. Special relationship stuff here. On this diagram, Fg and Fn are equal. And this is actually the only one of the diagrams where that's actually true. But if you notice the way this is kind of set up, Fg and Fn, they have to be kind of canceling each other out. They have to be balanced forces in the y direction because this object isn't being pulled down and accelerated or accelerated in the upward direction. So Fg, Fn equal in this diagram. That kind of helps with some of the problem solving. And likewise, if the problem states that the object is moving at a constant velocity, then we can also say that we know that Fa and Ff have to be equal as well. The problem has to say that though, so read the problems carefully, and if you see that, I would probably underline it or circle it. That's a pretty important piece of information, so look out for that. All right, so that's diagram number one. Let's switch over, let's do number two. Number two is still a horizontal surface, so still this, still got our object, dot in the center, that sort of thing. This one is going to be being pulled at an angle though. So you can see why there's a need for this diagram. We don't always apply forces at perfectly parallel angles and things like that. So this is going to be our applied force at some kind of an angle. Gravity still working straight down. Normal force is still pushing up on this object, just like in the first diagram. But some people like to draw it up here, which is perfectly fine. Some people prefer to draw it down here, which I'm going to do in this picture. Still points up. There's Fn. So you can see my arrow there. It's still pointing upwards. It's still perpendicular to the surface, which it needs to be. It just makes this area less congested because we're going to have a bunch of stuff up here. But if you prefer, you can still feel free to draw it up here. Either way is fine. So we can kind of see, I think we've done enough triangle work by now that we've got this right triangle that's going to develop here. Fa is being applied at an angle, so I'll put theta here. And so because it's being applied at this angle, it means there's going to be a component that's in this x direction and a component that's in the y direction. So these two things. So we can actually name these two forces as well. This force here, because it's parallel to the surface, is actually, that's what it's called. It's called Fp, force parallel. And then this one, because it's a force in the upward direction, is just called F up. So that kind of defines itself. So you got force parallel, and then you got the upward force here. So two components to the applied force since it's at an angle. And if this thing were moving to the right, then that would mean that friction would be acting to the left. So we can put Ff on there as well. So there's free body diagram number two. Definitely more complicated than the first one. You've got 6 forces here instead of just 4. Also more complicated on this diagram is that Fg and Fn are not the same thing. So don't make that mistake. It's only in the first diagram that FG and FN are equal. The reason they're not equal here is if you look at the numbers of forces that we have in the upward direction, we've got this guy, and then down here we've got normal force. We actually have two forces that are acting up and just one that acts down. And so if you think about this, this object is not accelerating down, it's not accelerating up. So the upward forces, so these two guys, have to equal the downward forces, which is Fg. So they're balanced forces. So it kind of sets up a way, if you understand that, it gives you a way to solve for normal force. So we can do that. We can set this up and say, okay, well, normal force is just going to be Fg minus F up. It's whatever force is still unaccounted for in the upward direction after we've taken F up into account. So you'll need that little formula to solve that out. Sometimes that's a lot of steps because you have to solve stuff up here first to get your F up. You will have to know Fg before you can plug in and solve for normal force. So that one's a little bit of a tricky one. We can do the same constant velocity situation. If the problem says constant velocity and it's diagram 2, then that would mean that this force, Fp, has to equal Ff. So that would give us a way to get to those forces if we need those. So Fp and Ff are equal if the problem says constant velocity. So be on the lookout for that. I think that's it for diagram number 2. The last scenario, work our way down here, will be if, we'll call this number 3. If your object is sitting on an incline or a hill or a slope or any of those things, so it would look something like this, then you can go ahead, Fg, still going to be downward. Normal force, remember the way that it's defined, perpendicular to the surface. Here's the surface, so it's actually going to be working this way. Totally fine on this one to draw it up here. It's kind of helpful to draw it down below here though, because it's going to help us set up a triangle to help us solve some of the math that's involved. So let's call that normal force. And then you can hopefully see that triangle kind of developing between normal force and Fg. I'm going to go ahead and connect them. Put our little 90-degree marker in there. So you've got a 90-degree triangle there, which is nice. That's going to give us some alternative ways to solve for some of these forces. We'll get back to that here in a second. If this object's going down the incline, so it's like a sled going down a hill or something like that, then this downward force here, sometimes we'll call that applied force because it's a force being applied. It's being applied by gravity. It's still a portion of Fg, but sometimes we can call that Fa. Sometimes you'll see this called Fp as well because it's parallel to the surface, just depending on the scenario. But if this object is sliding down the hill, then acting up the hill, of course, is going to be friction. So we can label Ff going up the hill on that one. In terms of solving some of these things out, so I'm going to label this angle here, the angle of the hill, and then I'm going to label this angle right here. There's some geometry theorems that basically kind of prove that this triangle that is the hill, this guy, the big one here, and this triangle that we drew in with Fg and Fn are similar triangles. And if you guys remember your similar triangle stuff, the angles are the same. So if you know the angle of the hill here, then that's also the angle of this right here. So if you know one, you know the other. That's going to help you to get to this so that you can use some trig to solve out this triangle. The other thing to talk about in terms of geometry is finding applied force up here. I'm going to draw, and you may not want to put this in your notes, it's totally up to you, but let me draw it in and then you guys can take a look at it and see if you want it in your notes. You can draw this other triangle in right here. If you can see that. So now you've got Fg here, that's the hypotenuse, and then it shoots up here. Here's Fa, and you've got this, what I would call like the third triangle on this diagram. And if you remember your geometry, you've got interior alternate angles here. So this angle and this angle, somewhere along the line, you learned that those are the same. So if you know this angle of the hill, then you know this angle, and you know this angle here as well. So you can see, I'm just trying to make the case for that if you can solve out this triangle here, then this side right here is the equivalent to this side of this third triangle up here. That's important because this is the applied force. So as long as you kind of understand the math here and why this side equals this side, then probably what I would do is just label down here that that's the applied force, and then that way you could just run through and run like sine or something like that with this triangle to be able to solve out FA. And you don't really have a need to draw this third triangle. Totally up to you if you want to. But as long as you kind of understand that this side is the equivalent to up here, it gives you a way to solve for the applied force. So I know that's kind of a lot of geometry talk there, but that's just basically the setup, how we can prove, I guess, that FA here is the same as up here, and I think it helps with the visual with that triangle. So anyway, that's the applied force and ways to solve for it. So like if you're solving like normal force here, you might know FG, and you can just do cosine, solve Fn. Or you might know FG in your angle and be able to do sine and solve for FA. Or if you know two of these sides, like if you know FA and Fn, you can run Pythag, solve for your third side. You got all kinds of options, which is kind of nice with the triangle that's there. So anyway, that's that. Lastly, special relationship stuff on this one, we can do the constant velocity again, just like we've been doing on all these diagrams. So constant velocity here would mean that FA equals FF. That would make this thing slide with a constant velocity down this incline. Other than that, I don't think I'll write out any equations for like Fn or Fa or that sort of thing, other than just reminding you to just use sine and cosine to help solve that stuff out. So that's it. I think that's the run through of these diagrams. We'll be working some practice problems soon that will put some numbers with these, but this is kind of the starting point to understanding these. So let me know if you have questions.